Hi everyone, I'm Julia, the chemistry tutor, and today I am going to talk about buffers. So let's get started. Okay, so first I'm going to talk about what a buffer is. So a buffer is a weak acid and its conjugate base, or a weak base and its conjugate acid. I will talk about conjugates in a minute, and it resists changes in pH with small addition of acid or base, strong acid or base. Okay, so it has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. And the whole purpose of a buffer is to resist changes in pH when we add small amounts of strong acid or base to that solution. Okay, and a conjugate acid has, I'll go with conjugate base first, since that's what I talked about first. It has one less hydrogen than the acid, which makes sense because we know acids have hydrogens. So a base would have one less hydrogen. So a conjugate acid would have one more hydrogen than the base. Okay. And so all we're looking at is showing if they have one more or one less hydrogen. So for example, if I had HCO3 -1 and CO3 -2, that's a difference of one hydrogen. This one would be the acid, and that would be the conjugate base. Or if we called that the base, that would be the conjugate acid. Okay, so either way, that one's amphiprotic, amphiteric. It can be both an acid and a base, this one right here. Okay, if I were doing another one, let's go with nitrous acid. That is a weak acid. So that's my acid. His conjugate base would be one less hydrogen. That's my conjugate base. If I had, say, ammonia, we know that is not an acid, that is a base, right? Because when we talked about acids and bases, he's got a lone pair on him. So he's a hydrogen ion acceptor. So his conjugate acid would have one more hydrogen. Okay. Okay, so let's look at some combinations here and decide if these could make a good buffer system. Okay, so are these going to make a good buffer system? So remember, we want either a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay, so here, those are both strong, so that cannot be a buffer. Here, I have a weak base. Okay, we call weak base WB, weak acid WA. So I have a weak base, but that is not its conjugate, so that cannot be a buffer system. Here, I have a weak base. We can ignore the chlorides. That's a spectator ion. When you did net ionic equations, chloride is typically a spectator. In buffers, chloride is always a spectator. So your halogens and your group 1, they're spectators. You can ignore them. Okay. So here, I'm going to, oh, sorry, I didn't finish this one. So I have a weak base. And look, that's his conjugate acid. He has one more hydrogen ion. So yes, that one could be a buffer. If I look here, get rid of the group 1 metals. I have a difference of one hydrogen ion. Neither one of them is a strong acid or a strong base. So this is a weak acid. So that would be a buffer because this is his conjugate base. This one was a weak base. That NH4 was the conjugate acid. Here, I can also ignore group 2. In buffers, you can also ignore group 2 ions. Okay, so I have a difference of 1 hydrogen ion. This is a weak acid, and that is its conjugate base, 1 less hydrogen. So that could make a buffer. Here I have a strong acid. Even though that is its conjugate, that's strong, that cannot be a buffer. Okay, so those 3 could be buffers because I have a weak base and a conjugate acid here, a weak acid and a conjugate base here, and a weak acid and a conjugate base here. Okay, so just remember, bases, 1 less hydrogen. Acids have 1 more hydrogen, right? My acid has 1 more hydrogen than my base. My acid, 1 more than my base. Acid, 1 more than my base. Okay, so that's how we can tell if we can make a buffer out of the things that we've been given. Okay, so now I'm going to do some buffer equations. Okay, so we talked about what a buffer is. Okay, that is a weak acid and its conjugate base, or a weak base and its conjugate acid, resist changes in pH with small additions of acid or base. We talked about what conjugates are, that a conjugate acid has 1 more hydrogen, the conjugate base has 1 less hydrogen. Okay, so now when we're looking at a buffer equation, if it says write the buffer expression or equation, we can call it either an expression or I'm going to say equation because this is a balanced equation. Okay, for the acetic acid buffer system, okay, I take acetic acid. Anytime you are writing the equation for a buffer system, you take your weak acid or your weak base, you put it into water. It is an equilibrium because it's weak, right? It never goes 100% to products. And your acid donates the hydrogen ion and leaves behind the acetate ion. So now if I want to identify the weak acid conjugate base or the weak base conjugate acid, whoops, I wrote that wrong, weak base conjugate acid. Okay, if we need to identify those, we look at what's the difference of 1 hydrogen ion. Well, your water and your H3O plus are different, right? And we're looking over here. So over here, this was my acid, and that was my base. It accepted the hydrogen ion. Over here is my conjugate acid, 1 more hydrogen. And here is my conjugate base, 1 less hydrogen. Okay, so you can identify the acid-base pairs. If I write the buffer system for ammonia, ammonia is a base. He accepts a hydrogen ion. So again, we put it in water because that's what you do when you do a buffer equation. You put it into water. It is an equilibrium. In this case, that's a base that's going to accept the hydrogen ion and leave behind the OH. So this was my base, making that my acid because that donated the hydrogen ion. These 2 are a difference of 1 hydrogen. That's my conjugate acid because it has 1 more. This is my conjugate base because it has 1 less hydrogen. Okay, so something to recognize is you always have an acid and a base as your reactants, conjugate acid and base as your products. Acid and base as your reactants, conjugate acid and base as your products. Okay, and just to keep in mind, I could have written this as OH minus and NH4 plus. We really don't care what order they're written in, as long as they're both written over there. Okay, so for a buffer equation, you just put the weak acid or the weak base into water, have it give up or donate or accept a hydrogen ion, and get your products. Okay, and you always get your conjugate when you do that. You started with a weak acid, you got a conjugate base. You started with a weak base, you got the conjugate acid. Okay, and so when I make a buffer, I don't just put the acid into water and it's a buffer system. That's not what we do. We do make a buffer by putting in the weak acid and the conjugate base. I put that in as sodium acetate, and the sodium as a spectator, so I get my acetate ion. So all of that is in the same beaker, one beaker, and I put in the acid and the conjugate base. Or I put in the base and the conjugate acid. So for this one, I would probably use like ammonium chloride, because the chloride is a spectator ion. Okay. So when making a buffer, you put both of those things into the beaker. You have them both in there. So earlier I had written this one, the bicarbonate ion, and I said that that's amphiteric, amphiprotic. It can be either an acid or a base, right? So it can be an acid because it has the hydrogen in front. It can be a base because it has the negative charge that can accept a hydrogen ion. Okay, so if I were looking at this, I would have to tell you, I would have to say, like, write the buffer equation for the bicarbonate as an acid. Okay, so if you're doing it as an acid, it is going to donate the hydrogen. So water is your base. Water is going to accept that hydrogen ion and leave behind the carbonate ion. I've got my conjugate acid is H3O plus, my conjugate base, conjugate base is the carbonate ion. Right? These two are a difference of one hydrogen. These two are a difference of one hydrogen. Okay, now if I want to use it as a base, it is going to accept the hydrogen ion from water. So it's going to make carbonic acid and the OH. So here is my, this time we use that as a base, accepted the hydrogen. So water is my acid. So the difference of one hydrogen. Here's my conjugate acid. There's my conjugate base. Don't know why I keep writing base, conjugate base. Okay, so you can be asked to identify the conjugate acid-base pairs to write the expression. So you just put your weak acid or base into water. Water either accepts or donates the hydrogen ion, and you get the other part. If you added your base, you get your conjugate acid. If you made it an acid, you get your conjugate base. Okay, so the amphiprotic, or sometimes they call it amphiteric. Okay, that just means that it is both an acid and a base. It can donate hydrogens and it can accept hydrogens. Okay. Okay, let me look at what we need to do next. Okay, so let's say that I want you to give me the buffer system for hydrofluoric acid. It's one of your weak acids. Hydros have no oxygens. So hydrofluoric acid, we put them into water. We get our hydronium ion and our fluoride ion. Here's our acid, conjugate base. Here's our base, conjugate acid. Okay, so now if I say write or show, write the equation or show what happens when strong acid is added to this buffer. Okay, so what happens when a strong acid is added? Well, the conjugate base will react with the acid. So my conjugate base is going to react with added acid is always H3O plus. Strong acid, H3O plus. So I add my strong acid. My conjugate base accepts the hydrogen ion. So I get my acid and water. If I show what happens with a strong base is OH minus. Okay, so my acid part, right, my acid will react with that added base, making the fluoride ion and water. So I get my conjugate base and water. So to recognize when the buffer system reacts, when my fluoride reacts, right, if I added acid, I would be shifting that direction, making more hydrofluoric acid and water. If I added OH, it's going to react with that acid. No, I don't want to talk about it that way. Okay, I actually don't want to talk about it. We don't talk about the shift in equilibrium. We don't really shift when it comes to bases. We actually just write the reaction of what happens when it reacts. Okay, we don't really talk about shifts. And the thing to notice is this is a reaction. This is not an equilibrium. It's an arrow one direction. That is the reaction that is happening until it's neutralized all of that added acid and base. And then it goes back to that equilibrium right there. Okay, so your acid part of your buffer reacts with the base. The conjugate base part of the buffer reacts with the acid. It would be the same exact thing if we were doing the ammonia buffer system. So my weak base, and put it into water. I get my conjugate acid. And the hydroxide ion. Okay, that would be my conjugate base. Oh, wait, hold on. Hold on. I've got those labeled wrong. This is my weak base, making that the acid that's donating the hydrogen. That's my conjugate acid. That's my conjugate base, because difference of one hydrogen. Okay, so now if I add acid to this, I add a strong acid, because we're never adding weak acids. Adding a weak acid doesn't 100% dissociate. It does weird things. So we're always adding strong acids and bases to buffers. Okay, so if I add a strong acid, my conjugate base will react with it. I mean my base, not my conjugate base. My base will react with it. Because remember, these are the two important things, my base and my conjugate acid. Those are the important things in a buffer system. Okay, the two things that you put in. So if I add a strong acid, my base will react with it. Accepting that hydrogen ion and giving me back water. If I add an acid to this, my conjugate base will react with it. Sorry about that. If I add a strong base to this, forgot what I was doing for a second there. If I add a strong base to this, I'm adding OH minus, gives up its hydrogen ion. Okay. So again, recognize if you're adding an acid, you use your base, you get your conjugate acid. If you're adding a base, you use your conjugate acid and you get back your base. Okay, so we're always looking at the two important things in the expression. What are the two things that are going to react? This one, my conjugate base, up here, sorry, my acid and my conjugate base were the things that reacted, my acid and my conjugate base. Here, my base and my conjugate acid. So here, my base and my conjugate acid. Okay. Okay, so let's do a few more problems with this, okay? So it's asking us if it's possible to make two different buffer combinations from this. And that is amphiprotic, right? Because it's got a hydrogen in front to donate, it's got negative charge in back to accept. So what would be the two combinations? Well, it would be that with an extra hydrogen. Oh, okay, so this would be my base and the conjugate acid. Or if it acted as the acid, one less hydrogen is my conjugate base. Okay, and keep in mind, every time you add a hydrogen, you add a positive one. Every time you remove a hydrogen, you remove a positive one or add a negative one. Okay, so anytime you have hydrogens in front and charges in the back, hydrogens in front, charges in the back, it can act as both an acid and a base, and you can get two different buffer systems out of it. Okay, so now let's look at this buffer solution made of these two things. So we can ignore those group 1 metals. So we have the sulfite ion, because that's a weak acid. Or, sorry, that's the conjugate base. And we have the hydrogen sulfite ion, so there's my weak acid. There's my conjugate base. Okay, so write the reaction that shows what will happen when a strong base is added. So a strong base is going to react with the acid part of that. Okay, so my acid reacts with the added base, gives up the hydrogen ion, and gives us water. So now if we look at what happens when a strong acid is added, my base is going to react with it. Did the wrong thing there. It's going to accept the hydrogen ion. So, thing to recognize, if you react your acid, you get back your conjugate base and your water. If you react your base, you get back your acid and water. Okay, so you get back the only thing that's in that solution. What do we have down here? Okay, so if we're looking at the NH3, NH4Cl, remember we can ignore the Cl. So that's NH4 plus and NH3. So what is the acid part of the buffer? The one that has an extra hydrogen. The base part of the buffer is the one that has one less hydrogen. Okay, what if I gave you and this guy? Make that so you can read it. Ignore that group 1 metal. So here is my acid part of the buffer because it's got one more hydrogen. There is my base part of the buffer because it has one less hydrogen. Okay. So now if we're looking at this one up here, the reaction that shows what will happen when a strong base is added, well, your acid will react with it. So my acid reacts with the added base, giving up the hydrogen ion and making water. So what happens when a strong acid is added? Well, my base will react with that. And accept the hydrogen ion, giving me back my conjugate acid and water every single time. Okay, if you start with your acid, you get your base back. Start with your base, you get your acid back and water. Okay, so now if we look at this, what happens to the amount of these after a strong acid is added? Okay, so that's this one right here after a strong acid is added. So what happens, my ammonium, the NH3, my ammonia, the NH3, decreases, right? I'm going to use some of that up. And my NH4 plus, I'm making some of that, that would increase. Okay, so remember when I said that at the beginning, I'll go ahead and go back here, when I said that it resists changes in pH with small addition of acid or base? The reason for that is here on this one, if I continued adding, if I continued adding more acid and more acid and more acid and kept going and kept going and kept going, I would eventually use up all of that I put in that solution. Okay, so eventually I would use it all up and it wouldn't be there any longer to react with the acid. So then when I added more acid, now my pH would decrease because I'm adding more acid and I've used up my buffer. Okay, I have no more of my conjugate base in there to react with added acid. Okay, so you can overcome, right? If I keep adding acid, if I keep adding and keep adding, we will do what we call overcome the buffer. And then your pH will change. Okay, so it's small additions. I can't just continue adding acid or base forever and expect for it to buffer. It's small additions of acid and base. It only buffers for so long. Okay, let's do this real quick, and then I'm going to start working on some calculations, right? Because these are equilibriums. So if they're at equilibrium, we can do calculations with them. Okay, so I'll do some calculations in a minute. But here, this is telling us to write the formula of each of the following, one conjugate base of that. So it's going to be one less hydrogen. So NH3. Conjugate acid of this, which is going to be one more hydrogen. H2O. My conjugate base of this, so one less hydrogen. Remember, remove a hydrogen, remove a positive charge. My conjugate acid of this, so one more hydrogen. Okay, remember, you add a hydrogen, you add a positive charge. Okay, so it's just that simple coming up with your conjugates. Conjugate base is one less hydrogen and one more negative. The conjugate acid is one more hydrogen and one more positive. Okay, so we're going to do another one of these, and then we're going to do a bunch of equations with equilibrium. Okay, so if I were looking at, nope, I'm going to go back. I'll do that in a second. Okay, so we've got a buffer that is made with these two things. Ignore those group 1 metals. So we've got, that's our acid. There's our conjugate base. Okay, so show what happens when we add hydrogen and hydroxide. Okay, so if I add the hydrogen, which I always see that as H3O plus, same thing, right? So that's an acid, so my conjugate base is going to react with it. So my conjugate base reacts with that added acid. gives me back my original acid and water. If I add strong base to this, my acid will react with it, giving up that hydrogen ion. I get back my conjugate base and water every single time. Okay, if I add my hydroxide, my acid reacts with it. If I add acid, my conjugate base reacts with it. Mm-hmm. And by the way, you could have called this your conjugate acid and this your base. It really doesn't matter. It's kind of the same thing. Okay. Okay, so let me just go back and specify that, right? Because I could have said, oh, well, this is my base. And so my conjugate acid has one more hydrogen ion. Okay, if it's amphiprotic, if it can be either an acid or a base, right, it can be either one. Okay, so now let's look at some of these calculations. Okay, so if I'm looking at this buffer expression here, this buffer equation, the acetic acid buffer equation, okay, this is aqueous, this is a liquid, this is aqueous because it has a charge, and that's aqueous because it has a charge. This one, because it's an acid, it's aqueous. Okay, so water is a liquid, we're going to ignore it. So if I went to write my K expression for this, my Ka, it is my hydrogen ion times that acetate ion divided by the acid. Okay, so I could give you numbers for some of those and you could calculate the others. Okay, but here is what I want to point out to you, is recognize that these two concentrations are exactly the same. However many of these split apart, if I had 15 of these split apart, I would get 15 of those and 15 of those, right? So these concentrations are the exact same. Okay, so if we were solving for, if I told you that your Ka equals 1.8 times 10 to the negative 5, which it actually does for acetic acid, and I told you that your concentration of the acid was 0.026 molar, and I say, what is your concentration of H3O plus? Okay, so we know our Ka is 1.8 times 10 to the negative 5. We know we're solving for the H3O plus, but this is the exact same concentration, right? This guy, conjugate base, is the exact same concentration. So we could just call that X squared. Okay, so when you're working with buffers, when you're calculating the concentration of the H3O plus, it's the same as the conjugate base, so it's always H squared. And then 0.026. Okay, so we want to isolate the X squared, so we're moving that to the top. So I have my 1.8 times 10 to the negative 5 times the 0.026 equals X squared. Okay, so if I do that math real quick, nope, that's not true. Okay, I get 4.68 times 10 to the negative 7 equals X squared. I'm not doing sig figs yet. I'm going to wait until the end. So I need to take the square root of both of those, right? So the square root of that answer is X is equal to 6.841 and some numbers, 10 to the negative 4. And we had 2 sig figs in that number, 2 in that number. So we're going to go with 2. So 6.8 times 10 to the negative 4 molar, because it is a concentration. Okay, so we do that a lot. If this had said, what is the pH? You would have done the exact same thing. You would have calculated the concentration of your H3O plus. Now you would have just taken the negative log of it to get the pH. And I get 0. Oh, that doesn't seem right at all. Nope, I took the square root of that. I don't know what the heck I was doing there. Okay, so the negative log of that 6.8 to the negative 4. I get 3.16749, and we had 2 sig figs. So in our logarithm, 2 decimal places. Remember, we talked about that when we did pHs. So I'd call that 3.17. It's my pH of that. Okay, there's my concentration. Okay, so we can do that with buffers. Okay, we can do that. Okay, not with a buffer. I'm sorry. This was just a solution of acetic acid. I'm going to show you the difference of on the calculations in a minute. If it's a buffer, we actually use a different calculation for it, a different equation. Okay, before I do more of those calculations, I need to show you the generic buffer that we talk about, or the generic system. So a generic is if I just have some weak acid. Okay, that could be acetic acid, that could be hydrofluoric acid, it could be sulfurous acid, it could be nitrous acid. It doesn't really matter, it's just a weak acid. So all it is your H, and that is your anion. Okay, it's just a random acid, just a generic weak acid. Okay, if we put it into water, we get, we get H3O plus and an A minus. Water is a liquid. So my K for this, my generic Ka expression for any weak acid in water, is my hydronium ion times my anion divided by my acid, which is exactly what we did up here. Okay, I have my hydronium ion, my anion, and my acid. Okay, so we use that a lot, the generic expression. Okay, so I'm going to come back over here, and now we're going to do some calculations on this. Okay, so the thing is here these are solutions, not buffers. So we're just using the general equilibrium expression for this. Okay, and if we write the equilibrium expression, I put him into water. It's at an equilibrium. Water accepts that hydrogen ion, and I get left behind my anion. So if we write the K expression for this, it's the concentration of my H3O plus times that anion divided by the acid. Okay, which is the same exact thing as writing H3O plus times my anion divided by my acid. Okay, so what are we calculating here? We're calculating the pH, which means we need to know the H3O plus concentration. Okay, so we are looking for that, and we know both of those are the same concentration. So I have that my Ka, which they gave us, is 1.3 times 10 to the negative 5, is equal to my concentration of my hydronium and my concentration of that anion divided by the concentration of the acid. So we're solving for the x. The 0.1 moves to the top on the other side. Okay, so if I do that math, I get 1.3 times 10 to the negative 6 equals x squared. Now, if I take the square root of those, just double check myself here. If I take the square root of that answer, I get an error. So I did something wrong there. Huh. I don't know what was wrong with that. So the square root of 3. I get x equals 0.001140. Now we're going to take the pH of that. So my negative log of it. I'll do sig figs at the end. So negative log of that answer. And I get 2.9430 and some numbers. And we had 2 sig figs in our number given to us. We want 2 decimal places in that answer. So 2.94 is the pH of that one. Okay, and remember, because it's a solution, we're just using the equilibrium expression. Okay, so I've got sodium propanoate, okay, and the sodium propanoate, that guy. Okay, hold on just a second here. I had to think about that one for a little bit of a second. Okay, so do you agree with me that that is a base? Because it has a negative charge on it when I take the sodium off. Okay, so we need the Kb for this. And this is something I have not talked about. Let me pop back over here. So your Kw, which we learned when we did pHs, Kw of water is 1.00 times 10 to the negative 14. And that's equal to the concentrations of your acid times your base, your hydronium times your hydroxide. Okay, well, Kw is also equal to Ka times Kb. Okay, so if I know my Ka, I can divide Kw by it and get my Kb, right? Move that to the bottom on the other side. Okay, so let's look at what we're doing here. Okay, so this one is a base, so I need my Kb to do my calculations on this. Okay, so my Kb is going to be equal to the 1.0010 to the negative 14 divided by the Ka of the propionic acid, right? Because this is the conjugate base to that acid. So divided by 1.3 times 10 to the negative 5. And I already did this math. I get 7.692 times 10 to the negative 10. Okay, I'm going to worry about sig figs at the end. Okay, so we know our Kb is equal to, okay, so let's put this in water. So I have C2, C3. So I put my conjugate base into water. It's an equilibrium. Water accepts that hydrogen ion. Oh, nope, water gives up the hydrogen ion. Sorry about that. That's a negative charge. Okay, and so this one is equal to products over reactants. So my conjugate acid, or my acid, times my hydroxide ion divided by that base, that conjugate base. Okay, so we know that and we know that. We're solving for those, and those are going to be the same concentrations. They're both going to be X, because however much of this happens, we get that, the same amounts of those. Okay, so our KB, which is 7.692 times 10 to the negative 10, is going to be equal to my X squared, because those concentrations are the same, times the concentration of that propanoate ion. Okay. So I get 7.692 because we're multiplying. Sorry, I'm solving for that. I'm multiplying that to the top on the other side. When I do that, 7.692 10 to the negative 11 equals X squared. Now I'll take the square root of both sides. And my X equals, when I do that math, my X equals 8.77 times 10 to the negative 6. Okay, that is my OH concentration. We need to calculate the pH. Our question is pH. So our POH is the negative log of that. So my POH equals 5.06. And so my pH equals 14 minus that, right? So we're bringing in the stuff that we talked about when we did pHs. So when I do that, I get 8.94. And we had, in our numbers given up here, we had in that Ka that we used to get our Kb, that was 2 sig figs. So we're going to have 2 decimal places in our P. So 8.94. So I almost can't see this one. C is pure water. Pure water is 7.00. You don't even need to do anything with that. Pure water is 7.00. Okay, so now I have a mixture containing an acid and a conjugate base. This is a buffer. Okay, in order to calculate the pH of a buffer, okay, so the thing to notice is up here, I didn't have a buffer. I had only the acid. Here I had only the base. This one, I have both of them in it. So if I have both of them, that is a buffer. And the pH of a buffer, you use the Henderson Hasselbalch equation. And I don't know if I'm spelling this right. I have no idea if I'm spelling that right. Okay, so the Henderson Hasselbalch equation. Okay, and the Henderson Hasselbalch equation is that your pH is equal to your pKa plus the log of your anion over your acid. Okay, I always remember it's the log of AHA. 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 It's the log of AHA. A over HA. Okay, so they gave us our Ka of the propionic acid up here. That was 1.3 times 10 to the negative 5. So your Ka, 1.3 times 10 to the negative 5. Okay, so to get our pH, we need our pKa. Remember, P is just negative log. So it's the negative log of that. Okay, so my pKa equals, oh, okay, I'm going to go ahead and finish this, but then I'm going to show you that we actually didn't need to do all of this work. And there's a reason for that. So negative log of 1.3 to the negative 5. Okay, so my pKa, this has 2 sig figs, so I'm going to have 2 decimal places. Okay, is 4.886, so I'm going to call it 4.89. Okay, so my Ka is 4.89. I didn't need to do all this math, and I'm going to show you why in a minute. So it's 4.89 plus the log of my base, 0.100, over my acid, 0.100. Okay, this is 1, right? Do you agree with me? 1.00 divided by 1.00. This is the log of 1. The log of 1 equals 0. So if your concentration of your acid and the concentration of your base are the same, if those are equal, then your pH just equals your pKa. Okay, because this right here, this whole term right here is 0. So my pH equals my pKa, 4.89. Okay. So when you're doing these, take a look, and if those concentrations are the same, you don't actually need to do any of that math because the log of 1 is 0. It just goes away, and your pH equals your pKa. Okay, so pH equals pKa if the concentrations of the acid and the conjugate base are the same. Your acid, which is Ha, and your conjugate base, which is the anion. Okay. So if those concentrations are the same in a buffer, you just have to get the negative log of your Ka, your pKa, and you're done. Okay, so let's look at this one. So this one is a solution, and it does not have a bunch of things in it. It only has the one thing in it. And do you see that that is, they gave us a Kb, so that means that this is a base. Okay, again, we're calculating the pH of these. Okay, so I know my Kb. Well, let's go ahead and just put that into water just to see. I'm going to come up with a generic equation in a second here. Since that is a base, it is going to accept the hydrogen ion. And it's the nitrogen that accepts it, so I'm putting it over there. Okay, so my Kb is going to be equal to my, oh, here it is. So it's going to be the Ha times the OH minus over the A minus is what that's going to be. So it's going to be my products, which is my acid, my conjugate acid, I guess that is. Nope, I'm going to leave it as an H. I just think it makes more sense. Okay, so my acid times my OH divided by that base. Okay, so we know our Kb, 1.1 times 10 to the negative 8 is equal to, I'm solving for this, that OH, because with that, we can get POH and then get pH, right? So we're always looking at the OH or the H3O plus on these. And this is the exact same concentration. Those are both X. So it's equal to X squared over the concentration of that. Okay, and when I do that math, I get 1.1 times 10 to the negative 9 equals X squared. When I take the square root of both of those, I get, I don't know if I have that answer in front of me. Let's look here. Oh, yep, I do. So I get, oh, hold on here. Hold on here. Something went right. Okay, I'm just going to calculate that because something went wrong on my paper. So take the square root of 0.1 second to the e negative 9. I get 3.3166 and some other numbers times 10 to the negative 5. And oh, okay. Something seems really wrong on my paper here. I did something weird. Okay, so when I do that, that's going to be equal to my OH, correct? Okay, so my POH is going to be equal to the negative log of that. And we'll do the negative log of that answer. I get 4.479. Okay, so my pH is going to be equal to 14 minus that. And when I do that, I get 9.52. Okay, and we are at up here. We have the 2 decimal places. So this is, I'm in 2 sig figs. So this is going to be 2 decimal places. Okay, and if I had rounded here, that would have rounded to an 8, and you would have gotten the same answer. Okay, and so now this one, this is the acid, oh, sorry, this is the base for that. Oh, okay, this is the acid for that, because when you look, this one has 2 hydrogens here. That one's got 3 hydrogens. It's got 1 more hydrogen. That's the acid. And we can ignore that chloride. If we ignore the chloride, that's got a positive 1 on it. I don't know why that keeps going away. Okay, so this is an acid. So we are looking at, if we put that acid into water, okay, and again, it's just my acid, my hydrogen ion, times that base, that anion, divided by the acid, right? Because this has to be the acid because it has 1 more hydrogen. That is the conjugate base. Okay, so we know our Ka, and they gave us Kb. Okay, so we know that our Ka is going to be equal to the Kw divided by that Ka. Okay, so my Ka is, let me just do that real quick. Okay, so I get 9 point, I'm going to be 2 sig figs there. So I get 9.09. So 9.1 times 10 to the negative 7 is my Ka. So now I can plug them in here into this equation here. So my Ka is equal to, these are the same concentrations, right? X and X. So my X squared over concentration of that guy. When I do that, I get 9.1 times 10 to the negative 8 equals X squared. Take the square root of both sides. And my X equals, where are we here? So I got that answer, square root of that I get 9.534 times 10 to the negative 4. And that is the concentration of my H3O plus. So now we just take the pH of that. So negative log of that. And I get 3.02. I should get 3.52. Hold on a second here. Okay, I know what I did wrong. I actually took the square root of that instead of the square root of this. Okay, so the square root of that is 3.016 and some other numbers, 10 to the negative 4. That's the H3O plus. So my pH is the negative log of that. And when I take the negative log of that, I get 3.52. There we go. That's better. Okay. So I'm just going to do a comparison here. Okay, on this one up here, we knew that this was a base because they gave us the Kb for it. Okay, so we calculated our Kb. We used our Kb to calculate our OH, because it's the OH that's in there. We got the POH, and then we got the pH from that. This one had that extra hydrogen on it, so that was an acid for the base that was above. So because it's an acid, we have to use the Ka. So we had to get the Ka first, and then plug it all in. This one, because it was a Ka, it solved for that acid concentration. So then we just got our pH of it. Okay. So pure water again, 7.00. And now I have a mixture. Okay, so I've got a mixture of that base and its conjugate acid. So because it's a mixture, it is a buffer. Okay, so this one, I'm going to go ahead and show you. These are equal concentrations. So your acid and your conjugate base are equal concentrations. So your pH equals your pKa. Okay. And they gave us our Ka up here. We got our Ka up here. So our Ka up here, 9.1 times 10 to the negative 7. So our pKa is a negative log of what I just said there, 9.1 times 10 to the negative 7. And when I do that, I get 6.04. And I had 2 sig figs here. I have 2 decimal places here. Okay, because your acid or your base and your conjugate acid were the same concentration, your pKa is equal to your pH. Okay, so now we've got buffered solutions. Now they're not the same concentration, so we're going to do the real calculations. Okay, so these are buffered, and if you didn't know they're buffered, I've got acetic acid and acetate. Okay, and if you don't want to come up with the formulas for those, you can use the generic expression that you know your Ka. Oh, we're not even using Ka because we're using the Henderson Hasselbalch equation. pH equals pKa plus the log of AHA, your anion over your acid. Okay, so they told us this over on the earlier page, or maybe they didn't, but the Ka for acetic acid is 1.8 times 10 to the negative 5. Okay, so my pH is going to be equal to my pKa So my pKa is the negative log 1.8 times 10 to the negative 5. Oh, that's not right. I get 4.74. And since we're at 2 sig figs here, we want 2 decimal places in that logarithm. So 4.74. So my pH is going to be equal to that pKa plus the log of my anion, which is the acetate, over my acid. And when I do these calculations, I just get my logarithm first. So I just have my log of 0.25 divided by 0.1, and then I add that to 4.74. So for this right here, I had gotten 0.39794 and some other numbers. And then when I add it, that whole thing, I get 5.1379. Again, we are at 2 decimal places in our logarithm. So 5.14. Okay. And something you can do to take a quick look at this to make sure you're on the right track, that you're doing it correctly. Since this is your base and this is your acid, okay, you've got more base than acid, a higher concentration of base, which means that it should increase the pH. Your pH should go up because you have more base in there. So we're always comparing it back to the pKa, and my pH went up. So I probably did that correctly. It makes sense. If there's more base, you're going to have a higher pH. Okay, so let's look at this next one. So again, I've got acetic acid and sodium acetate. So we're using the same. We know our pKa is the 4.74 that we calculated above. So this one is going to be my pH equals 4.74 plus the log of my AHA, so my anion, over my acid. Oh, goodness. Okay, so I'm going to do that logarithm first. And that gives me a negative 0.3979 and some other numbers. Now I add that to the 4.74, and I get 4.34. And if you look here, here's your base on top, here's your acid on the bottom. I've got more acid, so I should be decreasing the pH from my pKa. And my pH went down, so I probably did that correctly. Okay, so now looking at this one, we've got acetic acid and sodium acetate again. Okay, so again, Henderson Hasselbalch, it's the acetic acid. So our pKa is still 4.74 because it's the same acid. And we're going to have, oh look, they're the same concentration. Since they're the same concentration, my pH equals my pKa. So 4.74. Okay, save yourself the calculations. If you don't have to do the calculations, don't do all of those calculations, because if they're the same concentration, remember, exact same concentration, the log of 1 the log of 1 equals 0. Okay, so this next one, I actually had to look up the Ka for this because it didn't give me the Ka, and I think this is the correct Ka, so it's the one that I'm using. Or actually, I'm going to use a KB for this. I'm going to use a KB for this. And yep, I'm going to use a KB for this. Okay, because that is a base, and you see how this one has an extra hydrogen. So that's a base, and that's my conjugate acid. Okay, so I'm going to go ahead and put that into water just so we can see our equation. So that's a base. It's going to accept the hydrogen ion, leave behind the hydroxide ion. So our Kb, and I looked it up. Kb is 4.3 times 10 to the negative 4. Let's see, how did I do this? Oh, I know how I did this. Okay, I actually did this a little bit differently. I'm not using that. Sorry about that. If we look at this as this is our acid and that's our base, and we're just using the same exact process that our pKa is equal to the pH plus the log of AHA. We know that this is our acid. Okay, that's our, let me erase those. Looking at these up here, this is our HA, and that's our A minus. Okay, so if we're looking at it as that, we need a Ka. So our Ka is equal to Kw divided by Kb. And when I do that, I get 2.3 times 10 to the negative 11, and that's my Ka. So, goodness. So my pKa is the negative log of that. And when I get my pKa, I get 10.63. Let me just double check that. So negative log of 2.3 second EE negative 11, 10.63. Okay, so my pH, I wrote those exactly backwards. Sorry about that. pH, pKa. So my pH equals 10.63 plus the log of my base over my acid. Okay, so when I do that, 0.5 divided by 0.25. For that, I get 0.3010 and some other numbers. Add it to the 10.63, and I get 10.93 is my pH for that. Okay, so let me talk about that. Oh, hold on a second. I may have calculated something wrong. Okay, I'm back. Yeah, I miscalculated that on my paper that I had over there. So I get 10.93. So my pH increased, and I have more base than acid. So it makes sense that my pH increased, 10.93. Okay, and I think I've got one more of these, and then we're probably going to call it a day. So I've got, again, I'm at acetic acid, so we know the Ka for acetic acid is 1.8 times 10 to the negative 5. So we've got a buffer system here because we have our acid and the conjugate base. So we know pH is going to be equal to pKa plus the log of AHA. Okay, so we calculated this earlier. Let me adjust. So negative log 1.8 negative 5, 4.74. That's what I was thinking. So that pKa is 4.74 plus the log of my anion, 0 over my acid. Okay, and when I do that, this gives me negative 0.39794 and some numbers. Add that to my 4.74, and I get 4.34. We had the 2 sig figs, so 2 decimal places. So 4.34. And yeah, I think that's kind of it. So here, let's summarize a little bit. So on these, because you had both acid and base, it was a buffer, and the buffer is always the Henderson Hasselbalch, that pH equals pKa plus the log of AHA. Okay, and you didn't even have to write a buffer equation or anything for that. You didn't have to put it in water. You didn't have to do anything because you just identify your acid and your conjugate base. So this one here, I looked up here, just your acid and your base. I should stop saying conjugate on that because it could, if you looked at it as the base, it'd be a conjugate acid. If you looked at it as an acid, it'd be a conjugate base. So you're just identifying your acid and your base. Remember, you're ignoring halogens, like on that one there, we ignore that halogen. Let me do that again, make sure you see what I'm doing. So I'm ignoring that halogen, and this one has one more hydrogen. So it's the acid, making this one your base. So here's your HA, and here's your A minus. Okay, on this one up here, same thing. Here's my conjugate base, what we would call the A minus, and this is my acid, but they're the same concentration. So we just said pH equals pKa. Up here, to identify everything, here is my acid, here is my base, then I just plug it into the Henderson Hasselbalch. Here again, here is my acid, here is my base, plug it into the Henderson Hasselbalch. Here was looking at, this one's got one more hydrogen. So that's my acid. There's my base. And they were the same concentration. So we just said pH equals pKa. Okay, up here, looking at this one. Oh, this is just a solution. It only has one thing in it. So we're not using the Henderson Hasselbalch. So when it's a solution, here, let me go up over here. Okay, so when it is a solution of a weak acid or base, you're just using, and we're pretty much going to do these mostly with acids, right? You're using the fact that your Ka is equal to your hydronium ion times your anion. Oh, wait, something's weird there. Yes, your hydronium ion times your anion over your acid. Okay. If we're looking at a buffer, okay, this one you solve for the H3O plus using that X squared concept, right? Because these are the same concentration. Okay, so we solve for H3O plus, and then you take the negative log of that to get your pH. Okay, if you're doing the pH of a buffer, you are always, always, always using the Henderson Hasselbalch equation. Okay, and you know the difference because if it's a buffer, it has both an acid and a base in it. This one has only the acid. Okay, if it were a solution of the weak base, let me do this real quick because I didn't really do that. Okay, that's going to be KB. So that's going to be equal to the HA times the OH divided by the A minus. Okay, but we do that primarily. We do that with acids, solutions of a weak acid. Okay, on that paper, I think I did do a solution of a base. And if you do the solution of a base, you have to use that KB. Okay, and you get your KB and you solve for the OH, and then you get your POH, and then you get your pH from that. Okay. So I know that was a lot. I did a lot of things there, a lot of calculations, okay? But we went over what the definition of a buffer is. It's a weak acid and its conjugate base, or a weak base and its conjugate acid. Resist changes in pH with small additions of acids or bases. We talked about what conjugates are and good combinations, right? If it's not a weak acid or a weak base, can't be a buffer system. Talked about amphiprotic, which is both an acid and a base, can donate and accept hydrogen ions. We talked about the reactions of a buffer. When we add acid, the base part of the buffer reacts with it, like this right here. Right? When we add an acid, the base part reacts with it. When we add a base, the acid part reacts with it. Okay, and we talked about how to do the pH of weak solutions, right? If you're doing a solution, you're using the K expression for solutions. If you're doing a buffer, you're using the Henderson Hasselbalch equation. And yeah, I think that is all I have to say about buffers. So have a great day.